Everything is represented as a sequence of binary numbers in digital systems. Then how do we know what a binary number represents? Answer is, we need context to interpret it. For example, whether it is characters, numbers, programs, audio, or video, etc. Once the context is known, we need to know what standard to use to interpret binary numbers. There could be multiple different standards for the same context. Here we have several widely used standards. For characters, the ASCII is the most widely used standard. For example, 01000001 represents the uppercase A, and 01100001 represents lowercase a. For colors, RGB is one of the most widely used standards. For example, 1111 represents white, and 00000000 represents black. When it comes to signed integer, the 2's complement is the most widely used standard. For example, 0000, all zeros followed by the last one represent 1, and all ones represent -1. For floating point numbers, the IEEE 754 is the most widely used standard. 00111101 and all zeros represent a floating point number 0.25. Here's an example of which different information a 24-bit binary number can represent depending on context and standard. Here we have a 24-bit, which is 3 bytes binary number. First, let's assume that we know this binary number represents signed integer, which is context. Next, assume that we know that this signed integer is encoded using 2's complement. Now with that standard, we know what value the binary number represents exactly, which is 214,280. The second, let's assume that we know this binary number represents the color, which is context. Next, we assume that we know that this color is encoded using RGB. Now with that, the standard known, we know what color this binary number represents, which is this color. Third, let's assume that we know this binary number represents machine code, which is context. And let's assume that we know that this machine code is encoded using 32-bit x86 ISA. Now with that standard, we know what machine instruction this binary number represents, which is addl 8 parenthesis EBP register and EAX register. Let's take a look at the basic storage units, bit and byte. A bit is simply an each digit in binary representation. A bit is the smallest storage unit, and a single bit can represent only either 0 or 1. The byte is a group of 8 bits. With the 8 bits, a byte can represent 256 different things, from all zeros all the way up to all ones. Byte is the smallest memory access unit. There's no way to access a bit in memory directly. If you need to access a single bit in memory, you have to read a byte that includes that bit and do some bit level operations to get a single bit value. Here we have a 32-bit, which is 4-byte binary number. There are 32 number of bits or 4 number of bytes. From rightmost digit, we number them from 0. That is, the rightmost bit is a bit number 0, followed by bit number 1, and the leftmost bit is a bit number 31. Likewise, the rightmost byte is a byte number 0, and the leftmost byte is a byte number 3. The hex notation is widely used in computer systems and programming. It's because it's very convenient to convert to from binary numbers while saving space. The hex notation uses the base of 16, therefore from 0 to 8, 9, A, B, C, D, E, F. In programming like C, we use the prefix 0x to denote hex numbers. Because a single hex digit is equivalent to 4 digits of binary, it's very easy to convert between two. For example, 1111 is F, 0011 is 3, 1111 0011 is basically F3. Let's talk about memory. The program views memory as a very large array of bytes, referred to as virtual memory. Every byte of memory is identified by a unique number called memory address. On 32-bit machine, the memory address is 32-bit long, and it has a virtual memory space of 2 to the 32 bytes, which is 4 gigabytes. As you can see from the visualization below, from the left side, we have increasing memory addresses from 0 all the way up to FFFF, FFFF. Remember, each element stores a single byte, which is 8 bits. Memory, of course, is physically implemented with the hierarchy of different memory spaces in a pyramid shape. Let's talk about byte ordering, which is a system design choice. A byte ordering refers to the policy regarding the order of bytes within a multi-byte object in memory. Bits within a byte remain the same. We have two widely used byte ordering systems, Big Endian and Little Endian system. Big Endian system puts the least significant byte at the highest memory address, and Little Endian system puts LSB at lowest memory address. Sun, PowerPC, and Internet use a Big Endianness, while x86 use the Little Endianness. Here we have an example. We initialize an integer variable x with the hex 1, 2, 3, 4, 5, 6, 7, and the size of integer variable is 4 bytes. For this number, therefore byte 0, which is LSB, is 67, byte 1 is hex 45, byte 2 is 23, and byte 3, which is most significant byte, is hex 01. If we assume that x is stored at address hex 100, then we have MSB hex 01 is stored at the address hex 100, followed by the next byte 23 at address 101, and hex 45 at address 102, and finally LSB hex 67 at the hex memory address 103, which is highest memory address. On Little Endian system, it's exactly opposite. We have 67 at address 100, followed by 45, 23, and finally 01 at address hex 103.